Hello, folks. It's George Leoniak, and welcome to New Geometry. I'm very excited to be here today to share this video, a presentation about the flower of life and its relationship to the Fibonacci sequence. Recently, I discovered some awesome numerical relationships between the circle patterns itself and the sequence, the Fibonacci numbers, and I've tried to detail this and lay this out in this presentation. It's a little heavy in numbers in the beginning, but if you stick with me, I'll connect it all to some of the geometry that I primarily share on this channel. So let's switch over to the presentation. I think you're going to be really thrilled with this one. It's a lot of interesting information that I haven't seen anywhere else. It doesn't mean that someone else hasn't discovered this, because it is playing with the numbers a lot, but we're going to really go to some far out numbers in this one. So it should be really interesting and exciting. So let's just talk quickly about the two main things we'll be discussing here are this circle pattern of the flower of life. These are the 19 circles here. And there are one, and then 6, and then 12 around this sequence, adding up to the 19. We're going to expand that circle pattern out to much larger numbers of circles, and that's how we're going to make the connection and relationship to this sequence of the Fibonacci numbers. Now here, of course, this sequence goes 1 plus 1 equals 2, and 2 and 1 equals 3, and 3 and 5 equals 8, 8 and 13 equals 21, and so on and so forth. And the interesting thing about this is that when we divide the numbers, the larger one by the smaller one, it continually gets closer and closer to the golden ratio, which is 1.618033, and then it continues on with the numbers after that. So this will never precisely, and no matter how far out you go with these whole numbers, get specifically to the golden number. But it will oscillate around it forever once it gets to a kind of critical place. I guess that's right around 189 and 144 and 233. At that point, it kind of locks into the 1.618 relationship between this sequence of numbers. Now, I'm going to have to walk you through this a little bit piece by piece, just so we can build the language base that we're going to work with as we get a little bit further into the video. Because, as I already stated, this little chart is going to expand here at the bottom, and this is just the basic terminology that I'll work with here. And basically, each Fibonacci, each ring or rosette here is a sequence of circles. So at the second number here, this circle has 6. Now, I'm only starting at 1 here. I guess you could say that the radius here is 1 and the opposite radius is 1, so that would be 1 plus 1. And in fact, the way you would draw this out with the compass basically is to take the diameter of this circle, put the compass needle at the center, and then do your second circle. And then what you do is you hop over to the second circle and take the radius to the first circle, and that would give you 3. And you'll see how that progresses. But each rosette is basically, right now, the bands are the same number. So the band is going to add up different in a moment, you'll see. But each rosette has got 12 circles. This circle's got 12. This rosette has 12. This rosette has 6. And of course, this one is just the central circle. And then I'm doing the cumulative total of each of the circles as we go. So this one has 7, and then when we get to this one, it has 19. All right. Now, the next step here is to continue to expand that, and we 1 through 3, all the numbers are the same, but this is the first place where we have in the Fibonacci number sequence, because basically what I'm doing is going to put a circle, it's going to encapsulate those series of circles, all the circles that are in here, which are 61 at this point at the 5th Fibonacci number. But we skipped 4 here, right? So 4 is this series of red circles, but that is not one of the Fibonacci numbers, because at this point we're adding 3 plus 2. That will give us our new radius of 5. And this circle pattern to get out to the fifth ring is going to be included into that. So that's 18 circles that are in that fourth ring, another 24 in the last ring. So those rosettes, okay, the fourth and fifth rosettes, they add up to the circle band, which is this band right here, of 42, and that adds on to the rest of the circles that were already 42, 19, plus the 19 for the cumulative total of 61 circles, okay? So that's the method that is going to expand out to larger and greater circle pattern that you'll see in the next one. And then at some point, I just will not draw any more circles because we're going to get up into the millions. So one interesting thing here that maybe some folks haven't realized, it was new to me, and I've drawn this pattern a lot, is that really each rosette just increases. And remember, each rosette is 1 through 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the rosettes. Those only expand by 6 each time. So if we just look at without the circle pattern here, there's only 6 circles that are added to each rosette. So 6, 7, 8, 30 circles, 36, 42, then we're at the Fibonacci number 8. Then we go to 48, 54, 60, 66, right? Those are corresponding to 9, 10, 11, 12, till we get to 13. And just neat for those folks that love to do the numeric number crunching. Well, with that circle progression of adding each 6 circles, each rosette, we'll go from 1 to 6, and if we digitally compress, 12 will be 3, 18, 9, 24, 6, 33, 36, 9, and we'll get an infinite 3, 6, 9 progression by just adding 6 circles each rosette. I never really realized that because it just looks like there's so many circles each time around there. I didn't really realize just 6 new circles are added on in the 6 directions as it expands, and you just basically take the previous number that it would to the next, but adding 6. So just an aside, maybe there's something more someone can explore there. So I'm only going to draw out the number of circles on here to the 13th pattern because at some point it's going to get so many circles it would just look like a blob of gray on the page here. But at least you could see, let's just reiterate the language that I'm using here because we went up to the 5th already, right? So each circle is, each rosette is increasing by 6 circles, which is here in this column. I've brought it up to 72 here. And this is the important part, is these bands. So between 8 and 13, all the circles that add up within this band, from the previous band, well, there'd be 300 circles in that band. Now, the total number of that is going to be all the circles that were prior to that, which was at the 8th Fibonacci circle, which was 169. So now our cumulative circle number is 469. And what I started to do here was I wanted to see if the golden ratio was going to show up in these cumulative values of dividing the circles per band to the cumulative circles of the whole diagram. And at this point, at the 13th, it's 1.56. So not 1.618, but progressively, as you can see, getting closer. It's a little wonky in the middle, as we know it will be with the Fibonacci sequence. But as we get further out, we will progressively get closer. So let's see if that happens. So now we'll take the circles out. So hopefully you understand how the circles are progressing at this point. And these are the number crunching, basically, all the way from 1 and 1, we'll say 1, 2, 3, 5, 8, 13. We brought it up to 13. Now we're going to add all the rest up to 10,946. So this would be roughly the 21st Fibonacci number that I dragged the Excel addition out to. And here are the circles per band adding up and the cumulative circles that are adding up in the diagram. And here is the cumulative divided by the circles per band. So these are divided and from the right to the left here, or excuse me, left to the right. And we're starting to get close to 1.617 it bottoms out on. And I'm sure if we got further, it would probably push over the edge into the 1.618, closer to the golden ratio pattern. So so I didn't feel like, dragging and adding up more there. That's fine. I feel like this is headed in that direction. It gave me a view that it's going to converge somewhere around 1.618, as it should, because it's following these Fibonacci numbers. Um, but there was another pattern in here, and this is the amazing portion of this discovery. Up to this point, it was a lot of just number crunching, and yes, it probably would come close to 1.618 when we do this, the total divided by the added here. Now, what happened is I noticed at 144, just in looking at the numbers that are highlighted here, I saw 61777, okay? And 61777, of course, is very close to 0.618, right? So it's 1 divided by 5. And if we divide 1 divided by 5 divided by 5 again, that would bring us to 0.381 and the rest of the numbers. But in here in this sequence, we had 38,280 circles in that band, that prior band. And then we had 61,777 cumulative circles. So if we added those two together, right, and this is how the golden ratio works, you add the prior one to it, the prior value to the current value to get the future value. Well, that brought me to 100,392. That's only 392 more circles than 100,000, which essentially could be 1, right? And then if I take that number plus the 6177, that would give me 162,169, which is very close to 1.618, right? All roughly in the ballpark. And I wanted then to see if this number sequence carried on in relationship to the golden ratio, because these numbers are showing me golden ratio numbers right here, just in the circles themselves. So that was a bit of, it was a bit mind-blowing. So we went way beyond the 19 circles or the 469 circles, the 359 circles, 359 million circles out in the circle pattern of the flower of life design. Now, another way to look at this data here is to, in this previous one, I was dividing the circles per band, right? So those are the band of circles to the total. But let's just look at the cumulative circles from the 61777 to the next Fibonacci number below it, to the next Fibonacci number below it. And that's this set sequence of data. So I'm just dealing with the Fibonacci numbers. I'm not including the band of circles. And when we do that, the Fibonacci numbers will start to converge around phi squared very closely, 2.618. So if you took phi and squared it, 1.618, you get 2.618. 033. So these numbers right in this section around the 2,584 mark and the 4,181 mark, when we divide those two, we come up with very close to the phi squared. So now remember, this is just me playing with the circles and the expansive pattern, and we're getting the golden ratio showing up in the cumulative value of the circle totals. I didn't think this would happen like this. It could have been any number of circles, and in fact, I tried some other geometric patterns, like a square view expansion of the circles into the 4 directions, and I didn't come up with the numbers adding up around the golden ratio like this. So my last comparison that I wanted to make here was taking the golden ratio, now this is not the circles, this is actual values of the golden ratio. And what I did was I removed a lot of the rest of the digits here and just correlated them or made them the same length as these previous numbers that we'll see in this here. So they're the same length here. So we're going to make a comparison between these golden ratio numbers, right? Phi squared, phi cubed, right? We're going to make that comparison. And here, just as a reference point, at the 144 Fibonacci number, this is the place where we have 0.38196 and 0.61803. Now, this says it's 1.61804, but remember, I'm now just dividing without the remainder of the the forever number that continues on and on and on. Just to show here, I brought it way down in its reduction here to the 0.00004, and that number should be this, and this number, 0.00002, should be this value. And if you divide those two numbers together, we're going to get the golden ratio. But if we can divide these two numbers, we get 2. So this is, I'm about to remove the decimal point here, and you'll see here in this next slide what I'm doing here. So this is a lot of numbers on this slide. So if you need to sit down or turn the video off for a moment and lay down, I understand. But let's just focus on one section of this. And if you feel like coming back to this and taking a better look at it, feel free to do that. So let's do 144 to 233. And this here is showing the FOL, flower of life circles, right? Those are 6177. Here's phi with the decimal point, right? 0.618. And now if we jump over to this one, now this is with no decimal. This is with the decimal. So this is what I did. I removed the decimal point. So it's 61803, right? So we removed the decimal point. And now we're going to divide the 6177 by the 61803 to see what the difference is, between those two, and come up with the percentage, basically, of the level of accuracy between those two numbers, and see how accurate this is when we go further out in the rest of the values. Because remember, these are all the golden ratio numbers with the decimal points above and below. And of course, when we go down this way towards the Fibonacci numbers where I'm really removing a lot of the decimal points, we're going to come up with 50, 25, 100, 70%, right? Those are going to be all over the place, but it's not until we get the 99, roughly around the 189 section to 144, this is the best values within this, is 99.95% accurate that we come up with that. And the next value, 100,392 to 100,000 would be 99.6. So we're definitely above a significant degree of accuracy within this. If we were to test this out statistically, I imagine, if we took an average of these numbers starting at a reasonable area, we'd come up with some sort of 99.4 or 99.3% accurate. It's showing me that this pattern is really uncanny. It's just amazing that it worked out this way, that circles in the pattern are going to, just a cumulative number of circles at each band, and an addition of bands and accumulating circles are going to add up to these numbers. Look, 425257 is, now we're at phi cubed, 42360. So we're only a couple thousand off there, and that really continues all the way out, all the way up to the 300 million area. We have 359 million to 357 million. So we're a few million off there, and that's big deal. But we are dealing with phi in the Fibonacci sequence and the golden ratio. Once again, I didn't expect these numbers to correlate this way, to give me something that looked like it was replicating the actual values of the golden ratio through circles. And that's the kind of takeaway. So before we switch to the geometry I wanted to show you in here, besides just these numbers, this is certainly a different video than I normally present. But these are the key takeaways, and it's really like, well, what are the odds of all this really working out? I'm not sure. But I it's probably golden ratio odds here. The values here in this section, I've just taken a few of those slides and taken some of the key points here. The values near the golden ratio, and they start to converge around 1.618. Okay, so remember, this is where a lot of the action happens in that slide, is between 144 and 233. 6177 and 3820 will add up to 100392, and that adds up to 1.162169. And of course, that is 0.381, 0.618, 1, and 1.618. That's how that relates to the golden ratio. Okay, and that's shown down at the bottom here. Now, this converging around phi, at this point in the game, when we divide the cumulative circles per the band to the band added each time, and remember, the band is just the circles that are added to the total of the previous one. We have 1.613, 1.615, and then as we go further out, skipped a bunch here when we're at the 21st Fibonacci number, we get to 1.617, and I imagine we go further, we'll get to 1.618. If we go further, I wonder if we'll overshoot it and how far it will get out as we go further and further. I don't have the mathematical Excel power to do that. Maybe there's some sort of, maybe this is easily done, or maybe we need some sort of supercomputer to add that up. I doubt we need that level of power to do this, but I just don't have the time and patience to drag those numbers out to keep adding them up. Because in just the 3 more numbers at 24, we're up to 46,000 rows to deal with. So, okay, and this was probably the one that was most accurate out of all of these, is that the cumulative circles, so now we're not doing the circle per band thing. We're just going, how many circles are in the Fibonacci number here? How many circles are in the Fibonacci number here? And those numbers, they're coming right in around phi squared, which is 2.618033. So we're really at these sequence of numbers here, Fibonacci numbers 2584 and 4181. When we divide those two together, we come up with the 2.618, very close to phi squared. And then we do the golden ratio comparison and getting close to the phi ratio here. So this is with the phi numbers with no decimal in here, because this would be 0.618, this would be 1 solid, and this would be 1.618. And these are the FOL circles. And this one in the middle here would be a circle band. And these two, 6177 and 1621, those are the cumulative circles at those, like in this sequence here. So if we divided 162, 169 to 6177, I believe that is in this chart here. What are we at there? That one is, we're coming up with 2.625. So getting close to the 2.618 at that point. But for this, what I was testing to just see if we divide the numbers across from no decimal to the flower of life circles, we come up with this accuracy hovering around 99.7 or 99.6 within this area. Okay, so great. I hope that was a lot of mathematical number, a lot of numbers in there, a lot of number crunching. Let's talk about the geometry for a little bit and just switch gears, because this is where my discoveries with this all started. And I wanted to get through the numbers first. Hope I didn't lose too many of your viewers at that point, because this is really an exciting part to me. Let me just correct the difference here. So this is a new version of the Fibonacci spiral that I came up with that correlates to this version of drawing the golden spiral, because basically what I did here was I expanded the golden ratio circles out from a small spot in the middle, or worked them in. And this one I expanded from a starting radius of very small circle. It wasn't one, but we're going to call it one for this. And we expand it out from there doing the 2 consecutive radii technique. So if I set my compass needle over here and then go to so from 89 to the 55 circle, which is here, then I have added 89 and 55 for a radius. I put it at the center, then I'll get my 144. Just to revisit just a few things here, maybe this will help. You don't have to draw the whole flower of life circles. It's not even necessary. You could just do it with the radius of your compass. But it was fun to add up all the circles. If we were to have circles on this, these would be the values. Of course, 144 is the 61,777 cumulative circles. This band of circles that would be in here would be the 38280 circles, and the 89 circle, right? The Fibonacci number with the 89th circle would be 2,304.97, right? So that's the value that gives us 2.618 between 23497 and 61777, or 2.62. Okay, so that's enough on those numbers. I'm done with that. The difference here, I guess the reason I did that is because this pattern over here isn't adding a band, right? It's just going 0.618, 0.318. The next number underneath it would be somewhere around 0.23 something, okay, way down in here. And we keep going smaller. But the way we're going to mimic this circle is, this is a really easy method that I came up with back in September to draw a golden rectangle. I mean, it's the best method I've ever seen to draw a golden rectangle, because all you need to do is just draw concentric golden ratio circles and just connect the outer points. In fact, it will create the outline of a golden rectangle, but we can follow this light line here is a golden spiral that is going to follow the outside. So it's not a spiral that's inside like we often see, inside each little square. It's going to follow the outside around. And I really prefer that way the golden spiral is constructed. Now, this point in this golden, this Fibonacci spiral that's following that, we could, pick this up and put this spiral over top of that, and it's going to, mimic that pattern very, very well way out here, right? It's going to look like an overlay very, pretty well. Because when we get further, and even better as we get to larger numbers, as we go further and further out. So, but of course, the difference here is going to be when we go in further to the diagram and zoom in, zooming into the center of this, if we, starting with numbers here are 1, 2, 3, well, what's going to happen there is that our spiral connector points, basically, because remember, the spiral is going to follow the outside of these 90-degree angle terms that are going around here. We're just basically following those anchor points for the spiral. What's happening here is that those are not going to be 90 degrees. In fact, they'll probably never be 90 degrees. They won't be 90 degrees because they're going to always converge somewhere around 90 degrees, because it's not a pure golden spiral like the one on the right with golden ratio concentric circles. It's furthest away, of course, at the beginning, because we're dealing with 1, 2, 3, 5, 8, and then 13. But you can see 82.9 in the angle here, 92.7, 89, 90.4, and then so on and so forth. It's going to always oscillate around 90, just like the Fibonacci numbers always oscillate around the golden ratio, right? And they're always somewhere a little bit above or a little bit below. It's going to do the same thing with these 90-degree turns. The golden ratio, of course, will always turn at those 90 degrees, the way the spiral goes here. And you can see the light spiral that I've overlaid here, kind of going towards the center. At some point, I just turned it in here, but it will continue on infinitely forever as we continue to divide by 1.618. Okay, so that was a spiral way to look at this. This is the way to compare these differences between the two spirals that were created from this technique. And then I came up with this idea of Fibonacci pentagons compared to golden pentagons. The Fibonacci ones are almost golden, and I believe if you did this hand drawn, which I did a few times, just out to the 144th circle. Now, it's not 144 circles. Basically, I mean the circle that represents the 144th Fibonacci number, which, remember, that means that there are 144 little circles along this line until I get here. So the radius of this is 144. And if I take the previous circle, the 89 circle, and I anchor it and create a vesica Pisces, basically, on the 89 circle, that will intersect the back edge of this. This is a way to make a pentagon. And of course, if I've got an arm here, I can use my compass to swing out to get the length here and then get the length here and, just create a pentagon like that. I did these just with the computer, just pulled them out to see the differences at the end here. So these are pretty close. They're somewhere around 108-degree angle at the top here. But as we go further and further in, we're at 108.1. And as you'll see when we go in, it gets a little bit more wonky. But at this point, if we're dealing with 0.618 and 0.381, we will always come up with 108-degree angles here when we take the previous 0.318 circle to create that vesica anchored on that point. That will always intersect the larger circle at this unique spot, which of course provides the ability to draw the pentagon. Now, hand-drawn, you're going to come up with some variability. It might not be accurate. In fact, you might draw it this way, and it might be more accurate with the Fibonacci circle method. But you know that you started with the golden ratio technique to do this. You just were a little more inaccurate with your technique to doing it. So I don't think you'll be able to tell the difference between when you do it hand-drawn, but there is a difference when you look at it with the accuracy of the drawing on the computer. So let's zoom down in here and show what I mean. So, of course, like it always is going to happen in the lower numbers of the Fibonacci sequence, because they're not getting close to 1.618 at that point in their division of 13 to 8. So if we're here, you could see, well, if I do the computer-generated pentagon, it's a little under. At 8, it's a little over. At 5, it's way under. And of course, these just get all over the place at the end here. Off of 2, it's well beyond the 2 circle. So that's what kind of happens with the Fibonacci pentagons at lower values. But at the higher values, you will not know, but it will miss the mark here. But if you're doing concentric golden ratio circles, which you can easily do hand-drawn. In fact, I primarily teach this technique of drawing the golden circle seed of life. I'm constantly talking about these golden circles in relationship to the Platonic solids and drawing the icosahedron and the dodecahedron, which we will take a look at in the next slide. But here you'll see this continuous progression of no matter these pentagons, they're going to be scale invariant pentagons all the way through. Okay, so the Fibonacci icosahedron, and compared to the golden icosahedron, and it's almost golden again because it's going to follow the same pattern. It's just always going to be ever so close. Even measuring this angle, this is 164.5, give or take, and this one's also 164.5. And this, of course, is the important part about drawing the icosahedron, which I talked about, the one version in Metron's cube, which we'll take a look at in a second, having straight angle, an equilateral triangle here, which really distorts the view of the icosahedron. But if we do follow Fibonacci numbers out to 144 to 89, and do connect that line, you will get that break in that equilateral triangle. And that is giving you a more accurate representative view of the icosahedron. Here, of course, with the golden ratio, these are going to maintain the golden ratio dimensions. In fact, you can't draw an icosahedron from this view without having two golden ratio circles. You may come up with a technique that don't have to draw two golden ratio circles, but if you want to draw an orthographically correct icosahedron, if you put your compass at the center of that drawing and check the radius between these two circles, they'll be golden ratio. So it's essential to the drawing. Now, of course, when we zoom back in, this is where we have our issues. Of course, 1, 2, 3 at the beginning of the Fibonacci sequence, or 1 and 1. Remember, that's what I'm calling the diameter of the central circle, 1 and 1, 2, 3. Then what we do is we produce the octacosahedron, which I'm now calling the icosahedron that is drawn in Metatron's cube, the octa-icosahedron, because this is actually an octahedron. And at this point in the drawing, it hasn't gotten to the point where it's going to start to bend that octahedron into the equilateral triangle, bends, but it does start to do it over here between 8 and 5. So if you do the method of expanding the circles with the two consecutive radius that I was discussing earlier, as you get out further here, between 8 and 5, you're starting to get closer to looking like this, right? With the golden ratio, because this one, no matter how far you go into these circles, here's only 1, 2, 3, 4, 5. Here's only 1, 2, 3, 4, 5. 1, 2, 3, 4. Yep, the 5 circles out. Then you still always have the same angle. You won't ever revert at some point back to the equilateral triangle. So that's a bit of a big difference between the two, but it starts to move you into the direction of a golden ratio version of the icosahedron. But let's just do a more fine scale test, even at the larger numbers, because this is one reason why I often get asked, because I have a few videos about Metatron's cube and the flower of life, or that pattern. Often a question is, well, how about if you expanded those circles way, 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 way out there? Would eventually we come up with a golden ratio relationship between those circles? And I think this now is the data that says, well, you'll eventually arrive at these Fibonacci distances that get closer and closer to the golden ratio, but it won't ever arrive precisely at 1.618. Maybe that will. I don't know if there's a number crunch out there that says, wow, we finally hit it. I don't know how far you'd have to go, or if it'd always be just somewhere in that long sequence of numbers is some digit off. That's really all it takes, is just one little digit off out of thousands of infinite number of numbers. So anyway, here's my test just to show, even at 144 to 89, I didn't draw larger circles. I just cannot have the ability to have enough drawing screen to do it. But what I did here, of course, what I often talk about is if you draw a pentagon that, remember, this pentagon is flat, the red pentagon is flat to you, but if you flip that over like a door back into the form, well, it's going to match up. This proportion should be golden proportion as it is on the one on the right. This length here, let's just say this is the length now, is 0.318. Well, this length should be 0.618 along here, okay? And if I didn't actually do the number crunching on here, I'm just going to use a visual analysis, which is tough to see at this point. But you might notice if you look closely at the sidelines, because what I'll do is I'll draw a parallel line just to see if it will be exactly on top of the edge of this hexagon, which represents the outside of the icosahedron. And if you have a keen eye here, you can see that it's just a little bit wider here, right, when I draw that line through here. So it's ever so close to phi, to being a perfect icosahedron. But let's take a look again. Fibonacci icosahedron, I've zoomed in a little bit. The blue little corner here is the hexagon portion of the this section right here, or this section here that I'm pointing to. This is this one here that I'm pointing to. And I guess I should move these. They're really on the insides here. Okay, those are the 2 points I'm pointing to. And you could see as we zoom in a little bit more here, it's a little thicker than this line that's overlaying it perfectly on top. Now, as we get further and further away, right, we'll get closer. That distance should decrease even more because we're only at 144 to 89 in the Fibonacci numbers. When we get greater, we might be just like a hair sliver, even less than that, than right over top. Now, this has nothing to do with having to be totally perfect. It is saying that, geez, the golden ratio is just perfection beyond belief in terms of how it works. And the Fibonacci sequence, as we know, is the closest that it can get to mimicking that type of pattern that deals with whole numbers. Any numbers you can start with, you can continue that sequence out and of adding the previous, the two values and getting the third. So that's the overall summary of this video of, what's the relationship between the flower of life and the Fibonacci sequence? Well, that's my analysis of how the circles themselves, these takeaways here, actually relate to the cumulative number of these little circles in the pattern as they add up, are going to start to give you the values of the golden ratio themselves. And that was a unique discovery that I was pretty much blown away by, as I had a feeling that the numbers would converge on them. I didn't know that it would start to give me the numbers of the golden ratio as well, right? The 61,777 circles and 100,392 circles are very close to 1 to 0.618, right? So very, very neat information. I hope that there was some interesting material in there that you found might want to follow up on or relate to the work that you're following out. I have a feeling that many of my viewers, have an interest in the crystal spiral, and I'm sure there's maybe some interesting dialogue that comes up around the patterns that are being shown here. And I might do a follow-up video relating some of this information to it. Felt like too much to put all that into this video. But I look forward to any comments. And as another note, as I wrap up the video, if you like this video, please subscribe. Feel free to contact me in the notes here with any questions or comments, or send an email to me. I'd be happy to discuss this material with you. And check out new geometry courses, not really related to this information per se, but drawing and learning sacred geometry will take you to a new level of your understanding and relationship to it, is making it a practical application in your life, so you start to see and understand and relate to the patterns rather than just trying to absorb all this information without the actual tactile relationship with doing it. So I have a whole bunch of courses there that help get you involved within the art and craft of geometry, drawing sacred geometry. So thanks so much. Once again, please subscribe, and I'll be back with another video shortly. So much love and peace, and I'll see you next time. Bye.